This is Cosmic Ray, the quantum mechanic. We're going to do some more biochemical molecules and stuff here. This is one used para-amino benzoic acid. You'll know it's known as PABA. This was once used as a sunscreen, but there's biological uses for this also. So one of the cool drawings that I came up with was a benzene ring here inside a carboxylic acid with the nitrogen head. Looks like an arrow, doesn't it? So I'm going to call this guy the little Steve Martin molecule with the arrow going in there. Another little thing we could do here, draw it as a fish. I'm going to come up with each molecule having a different kind of fish look to it. So if you look at this guy here, carboxylic acids, like our vitamin B3, is always good to have a tail. You got a negative field out here, you can just kind of picture the electromagnetic forces going like a fin swimming in the ocean of energy. A circle inside the hex, 6 carbons on these benzoic acids, benzenes, whatever they're going to be. 6 hexa, they call them, right? Well, instead of drawing the double bonds in like they do here, to a real chemist are easy, but for beginners, you draw a circle. So when you got a circle in there, you can have the color degradations, you can have rainbows, you can have black and white intensities changing. So nitrogen, remember our color coding, if it's always blue, we got a thing where we just draw the balls instead of the N and the H's and all this. Give the little fish here little blue nose. So when you see a blue dot in a circle here, that's nitrogen. So you got nitrogen and a carboxylic acid tail with a benzene in the middle. 3 different representations. So what's the beauty of this? When this molecule is written in a regular chemical form, the OHs are even written with the double bond up and a single and the H on the end, you know. Spectroscopists, remember, have shown us it's a double bonded, it's a hybrid orbital. These oxygens are the same distance away. There is no H proton on there. They call it H, but it's just the proton, remember? So we'll edit this, so I know I'm going to repeat myself, but we're going to say para-amino benzoic acid. Para, when you're on this ring, there's 6 different places it can bond to, right? Para is when they're totally on the opposite sides. So para, where on the ring are they? There's ortho and these others, right? Para opposite, far apart as they can be. Amino is going to be an N, nitrogen. Benzoic, that's telling us it's got the benzoic acid. Now where's the acid? You got the amino side, you got the ring, a hydrocarbon ring. The acid in this case is a carboxylate. Double bonds. Here we are with benzene. Now benzene, we should have started with this first, but remember I said there's an aromaticity to it. The aromatic properties are where the circle comes into the picture. So you can draw these any way you want. The traditional way is with 3 lines showing that there's an equivalent of 3 double bonds. And you can draw it this way, and then the next one, it's the other carbon that has the double bonds. Okay, that stuff's 100 years old to draw it with. The easiest way is with the circle, okay? And as you see down here, you'll see honeycomb kinds of situations where the rings get together and they form bigger ones and bigger and bigger and bigger. Well, for our case, benzene is just 1 ring. So there's 3 double bonds, which are drawn as 2 eyes in the mouth. So now, whenever you see in the middle of a big old, say, testosterone or estradiol molecule, if that's an aromatic ring, you're going to see Ben. Ben is aromatic. So again, see, when you draw the line structure, this was kind of disappointing because 2 of these is what makes naphthalene. That's the old mothball smell. Well, the 3 double bonds get to be on top, but the bottom one is sharing this middle one, so you don't get to draw the other line in there. So I was going to have this be like a husband and wife kind of deal, but you can't draw it that way with that. But when you take 4 benzene rings, then the way you can draw it with the double bonds being only on one, you got 2 smiley face people there. I think that's an anthracene. I probably shouldn't even be saying what I think these molecules are that I learned 30 years ago. But you can get more rings together. So here, 4 of these together with 2 smiley faces. One of those isn't smiling, huh? I'm not going to say anything about having a married couple out of them. This, I hate to say I'm really pushing it, but I'm trying to come up with artistic ways of drawing molecules. There's just the oxygens are so far away from the rings. The nitrogens are in these rings, and it'll kind of take the look of, if you remember purine and pyrimidine, one ring has the bigger name, so one ring is a pyrimidine, so 2 rings is a purine. So the caffeine double ring here, 6 and 5, is resembling the nucleic acids, adenine, and you remember, think, the 2 big capital letters, so adenine and guanine are the double ring structures. So caffeine looks a lot like your nucleic acid structures here, right? We got double bonded oxygens out there. You got methyls hanging off, the nitrogens. See, this is interesting. When I studied organic chemistry, everything you were studying was carbon. You had methyl groups, you had OHs, you had esters and ethers and every kind of thing. Now what you got is these methyls, CH3s, coming off nitrogens. They don't teach you that in organic chemistry. And that always tiffed me because I noticed as the end of the book of organic chemistry, you got a 2-semester course, giant book. The last 3 chapters are the best, neurotransmitters and stuff. That's where the nitrogen comes in. Nobody ever reads those. I'm done with organic chemistry. They sell the book back to the library, which is priceless because you know where everything in that book was. If you need to go look something up, there it is with your notes. So never sell your books back when you get to higher level courses. The introductory ones, take what you can get for them. So we kind of came up with, I guess you'd call it a turtle. Caffeine turtle. 2 nitrogens give them little eyes, right? The nitrogens are kind of offset here. You got the oxygens hanging off. But see, they're just colors now. So you don't even have to really look and think N, O, C, CH3. We know that blue is nitrogen. We know that green is oxygen. We know that green has the electronegativity around it, right? Methyls now, on the other hand, are the ones that don't like water. So look at the way that this is so evenly distributed. I've seen the caffeine molecule before. It was drawn with the lines and, you know, the way the standard chemistry textbooks have it. But this, I've got a feel for the molecule now. I look and I go, these methyls, hydrophobic they call them, don't like water, they're evenly distributed. You got one out there, one down there, one over there. You got the oxygens coming off this double ring structure with negativity out here. There's 2 lone pairs of electrons out there. And then down here, you got 2 lone pairs of electrons. Nitrogens, they got a lone pair of electrons up here, and you got these double bonds. So this ring is going to be flat. The methyls are going to be hanging flat, planar as they call it. The oxygens are flat. Caffeine is a pretty cool molecule.